The torpedo car did not look dangerous. It looked like a giant steel sausage on a rail car, sealed tight, barely glowing at the poor end. What it contained was 300 tons of liquid iron at 2,700 degrees, and it was moving through the yard at walking speed. If the track was clear, you were fine. The track was usually clear, but there was always something else on that track. If you are new to Steel and Sweat, this channel covers the machines and the men of American industrial history, the things that built the country and what those things cost. Subscribe and leave a comment below with the next story you want us to dig into. This is the story of the torpedo car, the machine that moved liquid iron through the Pittsburgh steel district, and the men who worked in yards where 300 tons of metal at 2,700 degrees was a routine presence on the track. The torpedo car moved through an active steel mill complex. The track ran past casting floors, locomotive yards, and the work paths of men who crossed it dozens of times a shift. It ran continuously, because the blast furnace it served ran continuously, and the liquid iron it carried could not wait. But here is what the production logic of an integrated American steel mill makes clear, and what the men who worked in those yards understood without being told. The torpedo car was not the dangerous machine in the yard. Everything about its design was built to make it safer than what it replaced. The danger was not in the car. The danger was in the relationship between the car and every other thing that was happening in the same space at the same time, on a track that ran through the center of one of the busiest industrial complexes in the world. To understand what the torpedo car was, you have to understand what moved liquid iron before it existed. The first method of transferring hot metal from a blast furnace to a steelmaking shop was the simplest: run it direct. A blast furnace cast twice per shift, and when the tap hole was opened, the iron ran out in a stream that glowed orange-white, filling the iron runners on the cast house floor before flowing into the ladles or mixers positioned beneath. At a large blast furnace in the Pittsburgh district in 1890, that pour lasted 20 to 40 minutes. The men who worked the cast house floor during the pour stood in radiant heat that singed whatever was in range. When the iron was in the ladle, it had to move. The open hearth shop waiting for it was not waiting in a convenient location. Carnegie Steel's Edgar Thomson plant in Braddock, which began production in 1875, was purpose-built to place its blast furnaces and open hearth shop in proximity. But even there, the distances required mechanical transfer. The method used before the torpedo car was the open-topped hot metal ladle car, a large open ladle mounted on a railroad flat car, loaded with liquid iron from the furnace cast, and pulled by locomotive to the steelmaking shop. The open ladle car worked. It also had failure modes that were visible every time it operated. An open ladle carrying 100 to 150 tons of liquid iron at 2,600 to 2,700 degrees was exposed to the atmosphere in its entire upper surface. Heat loss was significant, and in cold Pennsylvania winters, the temperature drop during a long transfer run could affect the iron's condition on arrival. But the more immediate problem was splash. Liquid iron in an open vessel responded to track irregularities, locomotive acceleration, and grade changes by moving. A ladle that was filled to operating capacity had liquid iron close to its rim. A bump on the track, a curve taken at slightly above the intended speed, or a sudden brake application by the locomotive crew, any of these could produce a splash event. Liquid iron at 2,700 degrees, leaving the top of an open ladle car, did not behave in ways that were good for anyone in the vicinity. But the torpedo car changed the geometry of the problem entirely. The torpedo design enclosed the iron in a horizontal cylinder mounted on a rotating trunnion system. The pour opening was at one end, small relative to the total volume of the vessel, and could be positioned upward during transit. The cylindrical shape distributed the weight of the liquid iron along the car's length rather than concentrating it in a single vessel. The enclosed design meant that track irregularities and grade changes did not produce splash because the iron had nowhere to go. The same bump that would have sent liquid iron over the rim of an open ladle car produced only a slight internal movement inside a sealed torpedo, absorbed by the geometry of the cylinder. A fully loaded torpedo car carrying 300 tons of liquid iron weighed, with the car itself, approximately 400 to 450 tons. It moved on a dedicated rail car designed specifically for the loads it would carry, running on multiple axles distributed along its length to manage the weight on the track structure. The locomotive that pulled it was a standard industrial switching locomotive of the kind used throughout the Pittsburgh Mill District, operating at a walking pace, typically 3 to 5 miles per hour, through the mill yard. Carnegie Steel began using torpedo cars at its Pittsburgh-area facilities in the 1890s, and U.S. Steel, formed from the Carnegie consolidation in 1901, standardized torpedo car operations across its major integrated plants over the following decade. The Homestead Works, the Edgar Thomson plant, and the Duquesne Works all ran torpedo cars between their blast furnace complexes and their open hearth shops by 1905. Bethlehem Steel at its south. Bethlehem Works in Pennsylvania and Illinois. Steel, at its South Works complex in Chicago, adopted the torpedo design for the same reason every other large integrated producer did. The alternative was the open ladle car, and the torpedo car was measurably safer in normal operation. But normal operation was not the only condition a torpedo car encountered in an active mill yard. The mill yard that a torpedo car moved through was not a dedicated transit corridor. It was a shared space that served every function the integrated steel plant required. Locomotive traffic from multiple operations used the same track network. Workers on foot crossed the yard tracks to move between buildings and workstations. Scrap trains, slag cars, and ingot molds all moved through the same network on their own schedules. Iron ladles returning empty from the open hearth shop past torpedo cars moving full on the same route, on track switches that required the locomotive crews of both to coordinate a handoff measured in feet. The switching engines that managed the yard moved continuously, coupling and decoupling cars, repositioning equipment, clearing track ahead of the torpedo run. At night, the yard glowed from the furnace stacks and the pour spouts of the cars themselves, and the locomotive headlamps cut through the steam and dust at ground level while the furnace flames backlit everything above. The yard of a large Pittsburgh-area steel plant in 1905 was a place where dozens of operations were running simultaneously, on a track network whose management depended on an informal system of right-of-way that gave the torpedo car priority by convention rather than by any physical barrier or signal system. How do you know the torpedo car is coming when you are crossing a mill yard track at night between buildings, with furnace noise filling the space around you and your shift beginning 4 hours ago? How clearly do you hear a walking pace locomotive approaching when the open hearth shop 50 yards behind you is venting and the hammers in the forge shop beyond the next building have been running since the start of the turn? Leave a comment below. If you are finding this history as important as anything we have covered on this channel, go ahead and subscribe right now and leave a comment below with the next story you want to see. The men who were killed by torpedo car movements in Pittsburgh-area steel mill yards between 1895 and 1915 were not killed by catastrophic failure of the car. They were killed in the ordinary operation of a vehicle moving at walking speed through a space that had too many things happening in it at once. The Pennsylvania Labor Bureau's annual reports on industrial accidents in Allegheny County document torpedo car and hot metal transfer fatalities across this period. The pattern in those reports was consistent. A worker crossing the track on a routine path, a torpedo car movement that was on its normal schedule, a sightline obscured by a building corner or another piece of equipment, a locomotive moving at 3 miles per hour that could not stop in a distance that mattered. The car that killed a man weighed 400 tons. 3 miles per hour and 400 tons produce a stopping distance that no signal or shout can close once the geometry has been set. But the catastrophic failure mode existed too, and the industry knew it. A torpedo car derailment carrying 300 tons of liquid iron at 2,700 degrees was an event in a different category from anything else that could happen in a mill yard. The torpedo's enclosed design, which made it stable during normal operation, also meant that a derailment did not immediately discharge its contents, but a derailment that rolled the car, or that breached the vessel, or that drove the pour spout into a fixed structure at the moment of impact, could release liquid iron in a volume and at a temperature that nothing in the immediate vicinity could survive. Liquid iron at 2,700 degrees moving freely across a mill-yard floor contacted ground moisture, drainage channels, and the standing water that accumulated in any industrial yard, and the reaction was immediate and violent. Steam explosions from iron and water contact at these temperatures moved with the speed and force of the iron itself. The derailment records for hot metal torpedo car operations in the Pittsburgh district between 1895 and 1920 are documented in Pennsylvania Railroad and Mill Company internal reports that became available through congressional investigation and later archival research. In 1904, a torpedo car derailment at a Monongahela Valley integrated steel plant displaced the car from its trucks and drove the pour spout into the ground, releasing a partial discharge that destroyed a section of the adjacent casting floor and injured 4 workers in the surrounding area. In 1911, a derailment at a Pittsburgh district plant resulted in a complete rollover of the car, the largest hot metal release event documented in western Pennsylvania operations to that date. The scale of the cleanup required was measured in days. What happens to the men working within 50 yards of the track when 300 tons of liquid iron at 2,700 degrees leaves the rail and the ground around them is wet? What does a man do in the fraction of a second between recognizing what is happening and the moment when the distance has closed? The physics of that question do not require documentation. The documentation exists anyway. But the torpedo car remained the standard. It remained standard because the alternative was the open ladle car, and the open ladle car killed men in its normal operation at a rate the torpedo car did not. The industry's decision to adopt the torpedo design was not an error. It was the correct engineering response to a real problem, and it saved lives that the open ladle car would have taken. The failure mode that the torpedo car introduced, a catastrophic derailment event, was rarer than the daily splash and overflow events of the ladle car era. The men who worked in the yards of U.S. Steel and Carnegie Steel in 1905 were safer with the torpedo car than without it. They were not safe. The distinction mattered in the engineering reports and in the company insurance actuarial tables. It was a different kind of distinction for the men who crossed those tracks. The torpedo car remained in standard use in American integrated steel operations through the middle of the 20th century. The design was refined over time, with better trunnion bearings, improved pour spout geometry, and more sophisticated locomotive control systems. But the fundamental configuration that was established in the Pittsburgh district by 1905 did not change in its essentials. U.S. Steel was operating torpedo cars at its Mon Valley plants into the 1970s, and some torpedo car operations continued at surviving integrated steel facilities in the United States into the 1990s. The blast furnaces those cars served are mostly gone. The cast houses where the iron was tapped twice a shift, the open hearth shops where it was converted into steel, the blooming mills, the rail mills, and the structural shops that turned that steel into product are gone. The entire integrated mill complex that the torpedo car was built to connect has vanished from most of the sites where it operated. The track they ran on is mostly gone. The yards they moved through, the casting floors, the locomotive sheds, and the open hearth buildings that framed their routes have been demolished or converted over the decades since the Pittsburgh steel industry contracted. What the torpedo car carried, the liquid iron that became the steel that became the bridges, the rails, and the structural shapes of the early 20th century, now lies in the ground and in the infrastructure all around you. The men who cleared that track built what you live in. If these are the stories that matter to you, subscribe to Steel and Sweat and leave a comment below with the next story you want us to dig into. Thanks for watching.